Here's our logarithmic expression that we're asked to express as a single logarithm using essentially the log laws that we know. The way I usually start these problems, I usually start with any values that I see sitting in front of these logarithms. So I see a 1/3 here, I see a 2 here. I understand with my log laws over here that I can take that idea that's in front of the logarithm and I can boost that up as an exponent. So real quickly, save myself a little writing, I cross out the 1/3, I make it a power here. I cross out the 2, I make it a power here. Okay, depending on my comfort level, we can do a lot of this at once, but if I just work left to right, I just take it a couple of logarithms at a time. I notice with the first couple of logarithms I encounter, I'm subtracting. So when I go back and I look at the subtraction idea, which would be right here, subtraction essentially creates a quotient. So to spell that out, I make this log base 3, combining these two logarithms as a quotient now of what I'm taking the log of. I'd have a over y to the 1/3. Just to make sure it's clear, it's a quotient that's being plugged into that logarithm. I might throw some parentheses on there. Now I haven't done anything with this part, so I'll just bring this along. But once again, depending on your comfort level, if you see that addition and you recognize that that just means we're going to have some form of multiplication you could attach on here, you could go ahead and piece it all together. So I do have addition. First item on my log law list with the addition means I have to create a product. So if I come back here, I would have log base 3, a single logarithm. I'm taking this portion times this portion because of the addition. All right, so putting this together with the multiplication, we've got a over y to the 1/3 being multiplied to the x plus 3 squared. Now, all of this is being plugged in the logarithm, and really we should clean that up a little nicer. I've got this quotient times this idea. Technically this is over 1, right? So let's go ahead and multiply the fraction out to simplify further. I'd have log base 3 of a times x plus 3 squared all over this y to the 1/3 idea. Now, if I write y to the 1/3, that's fine. But how's another way I could write y to the 1/3? Anybody know? There you go. You got a fractional exponent, we got roots involved. So some of these problems you might encounter some sort of root. You need to understand that root we can change over to a fractional exponent to help us with applying these laws. If you left it as y to the 1/3 though, that's fine too. But there's a review of how to simplify one of these expressions. Alright, first problem, first log equation we got to solve. We're going to deal with a logarithm with a base 4. X squared is plugged into that logarithm. That equals 3. If you have a logarithmic equation, and you know it's a logarithmic equation because you look at it, it's an equation and there's logs in there. Pretty hard to decipher, I know. You're trying to get the logarithms by themselves on each of their respective sides. If there's just one logarithm like I have right here, then I'm all set to go. I want to change this over to an exponential idea because that's what I'm used to dealing with when I do calculations. Okay, that's what I'm used to dealing with when I solve things. So how I would convert this over, since I have the single logarithm, I'd take my base 4, I'd raise that to a power of 3, I'd set that equal to x squared. I'm just applying the definition for the logarithm. So it's 4 cubed equals x squared. 4 cubed. I calculate that out. It's 64. At which point, if I'm solving for x, I take the square root of each side. When I take the square root of each side, I got to remember, since I'm solving, there's always that plus or minus aspect. So here it's going to be square root of 64 plus or minus 8. That is what x could be. I could plug back into the equation to check. Everything should work out nice and clean. We're still solving for x here. We'll stick with a single logarithm idea, but let's use a natural log this time just to review how natural logs work. Take the natural log of x minus 7, set that equal to 1. Let's assume here we're going for exact answers. If we're going for exact answers, we recognize with the natural log that there's this phantom e base, right? It's a logarithmic equation, so I want the logarithm by itself. I've got it by itself. So now I ride the merry-go-round, so to speak. I change this over to the exponential form. I'm taking e, I'm raising it to a power 1, setting that equal to x minus 7. From here, if I solve for x, if I'm going for an exact value, I can just leave everything in terms of e. It's e to the first, add the 7 over. Got e plus 7 equals x. There's your answer. So a slightly more intriguing problem here. We've got all these logarithms floating around on each of the respective sides of the equation. The goal is to basically create one logarithm on each side. To do that, we use our log laws. So on the left side of the equation, I notice I'm adding here. Since I'm adding, I'm going to take what I'm applying that natural log to, what I'm applying that natural log to, create one natural log where I've got the product of those two ideas. So x plus 2 times x. For step's sake, I'm going to write this. Can I multiply it out? Sure you can. And eventually, for where we're going with this problem, you'll see we'll want to. That's going to equal, on the right side of the equation, we've got two logarithms that are natural logs we are subtracting. So subtraction means create one logarithm, in this case natural log again, where we've got a quotient of these two ideas. So that'd be 18 divided by 6. And at this stage in the game, what I notice is that I've got the same natural log on each side. Now, if you have the same logarithm on each side, you can drop that logarithm out. Understand, I'm not dividing by the logarithmic notation because that's not allowed. It doesn't make mathematical sense. What I'm, in theory, doing is I'm raising this idea as a power on each side where I've got this base number of an e involved that will allow me to cancel it out. That's the long story. The short story, these can go bye-bye. If they go bye-bye, I've got x squared plus 2x, when I multiply that out, equals 18 divided by 6, 3. You've got a quadratic equation. So we bring everything to one side. We set equal to 0. Solving from here, looks like we could factor this, right? It's got to be 3 and 1. It'd be a plus 3 and a minus 1. We take our two factors, set each factor equal to 0, and solve. X would equal, first factor, we get negative 3. Brought to us by the second factor, we get 1. So our solutions appear to be negative 3 and 1. However, we have to be careful with these solutions whenever we're dealing with a logarithmic equation. See, you can't take a log of a negative number and you can't take the log of 0. So if you were to insert these answers back into the original equation and you see that you're taking the log of a negative number or 0 at any point, you would have to take that solution out. So notice what happens with this negative 3. When I take negative 3, I insert here, or here for that matter, you'd have the natural log of a negative value. Not allowed. So we got to take this guy out. If you would insert 1 in, though, 1 would create positive values, which would be good to go. So 1 would be our only solution here. That's the only catch on these logarithmic type equation problems. Okay, so we're switching gears here and we're going to solve an exponential equation very similar to the logarithmic idea. With logarithms, you're trying to isolate them on their respective sides. You're trying to create just one logarithm on each side. Exponential, same kind of thing. You'd really like the exponential part of it, and this would be the exponential part of it. You would like that by itself on its respective side. Since it is here, what you do is you apply a logarithm now to each side. And you do that because of the laws that you have. The laws that you have allow you to bring this power down if you apply a logarithm to each side. What we're going to do in this class consistently is we're going to apply a natural log to each side. So I'm applying the natural log to e to the 2x. I do that to the left side. I also have to do that to the right. Over here, natural log of 9. Again, the reason I did that, I want to bring this power down, so I have a law that will let me do that. So the 2x pops down to the front. You're left with 2x natural log of e now equals the natural log of 9. Does anybody remember what the natural log of e is? 1. Good. So that's gone. Meaning you have 2x equals the natural log of 9. Solving for x equals the natural log of 9 over 2, which we could calculate, but if I leave it as an exact answer, that would be good enough. All right, so example 5 here, very similar to example 4. We've got the exponential expression already by itself. So like I did on the previous problem, I'm going to apply a natural log to each side. I've got the natural log of 4 raised to a power of x plus 5. That equals the natural log of 3. So I'm doing that to allow me to bring down this power. So this power of x plus 5's got multiple terms to it. It's important I keep some parentheses on there to help me recognize that all of this idea gets multiplied to the natural log of 4. If you're solving for x, you got parentheses in an equation. You would distribute through to that set of parentheses, right? And normally we're used to just some normal looking number that we would distribute through. Understand the natural log of 4 is a value. So we can distribute that through. So I'm using the same strategies as I always would for any kind of equation I solve. Take the value, distribute through the parentheses. When I do that, whatever I'm multiplying inside here, just to keep it all straight, I'm going to multiply that to the front of this natural log that I'm multiplying through. That allows me to kind of keep everything separate between what I'm plugging into the logarithm and what should be multiplied to the logarithm overall. So x goes in front, plus here 5 goes in front. There's the natural log of 4 distributed through. That equals the natural log of 3, at which point I've got all my x terms, really just one x term, out in the open, and I want to get that by itself. So take this 5 natural log of 4, subtract it over, and if you're solving for x, this is now moved over, I'd be dividing by the natural log of 4, right? It's just a number attached to x. So if I divide that over, you've got x equals the natural log of 3 minus 5 natural log of 4 over natural log of 4. Now you could be wondering a lot of things at this point, aside from questions you may have about how I got here. But one thing we got to get out of our minds is this natural log of 4 idea canceling out. Cannot cancel that out. Okay, we've got subtraction up here. That's not allowed. If we divide this into this term, we'd have to be able to divide it into that term as well. Another thing, if I'm leaving this in an exact form, this is pretty rough. It's not a great form to leave it in. So what I might do to clean this up is I might use some of my log laws. Like take this 5, for instance, it's in front of the natural log, bump it up. If I bump that up, then I could take this x in the next step. Since I've got subtraction, I'd have the natural log of, with that subtraction, be 3 divided by 4 to the 5th power. And that's all over the natural log of 4. That's a little cleaner, even though it may not appear that way. The other thing is, if you're calculating this out, at this point, you could calculate what you have there. Just start punching some buttons, get an approximation. That'd be okay. But exact value would be what I got right down here. All right, hopefully a quick review here of how to sketch a couple of these graphs and get the region that's bounded by the two ideas. This is something that later on in the year is a pretty significant thing for us to be able to do. So we review it right now. Both curves, so to speak, these are graphs we should be familiar with. But one thing about sketching these regions that are bounded by curves that's important is you really need to find points of intersection when you do these. So off to the side, before I do the graph part, I find the points of intersection. And how I find that, go back to maybe some methods that I used yesterday when I was solving those systems. We talked about elimination as a possibility, but since these are not both linear, substitution might be a good way to go, especially since one of them is solved for y. All right, if I've got one of these solved for y, I can take what y is and I can just insert that into the other one for y. When I do that, inserting into this equation over here, I'd have 2x plus y would be x squared plus 2. If I want to show the substitution, I throw parentheses in there, but here parentheses really would not be necessary as I simplify further. That equals 5. Checking out what I have, it looks like I got a quadratic forming, so I'd want to get everything on one side. Starting with that x squared term, plus that 2x, bring the 5 over, so subtract over. Looks like something we factored earlier, right? One of our previous problems. We would have x plus 3 minus 1. So x would equal, from those two factors, -3 and 1. Meaning our points of intersection, we'd have 2 points. One point, x coordinates -3. Other point, x coordinates 1. Question is, how do we find the y's? Well, take your x coordinate, plug back into either one of these equations, probably this first one since it's solved for y, and you can figure out y. So I take -3, I plug in, I square that, I get 9. Got 9 plus 2, so this would be 11. Take 1, plug in, got 1 squared plus 2, that'd be 3. Since we went to all the work to find those points, let's plot those out. Got -3, got 11, and I've got 1, 3. Now if I recognize the two graphs I'm dealing with, one of them is a line, I only need 2 points to determine a line, right? That line's going to have to travel through these 2 points. So I could do all the slope-intercept form, right, and count it all out. In the end, though, it needs to go through these 2 points. So I've done that work. Let's go ahead and connect some dots. This would be 2x plus y equals 5. Now the other one is a quadratic, other one over here. So with that being a parabola and what we know about transformations, it's going to shift up 2 units, right? So key point on the y-axis I would need would be up here at 2. But then this curve also goes through those points of intersection. So drawing this parabola out, go through that point, come down here, go through this point. There's your parabola. There's your y equals x squared plus 2. Sketch the region bounded by the curves. Region bounded by the curves is everything contained between the 2 curves. So we get to do some coloring now. This makes all that hard work worthwhile. Red and blue make purple. So I've connected everything.